Alright, let's take a look at lesson 9.7, Similarity Transformations. So you can use a composition of rigid motions and dilations to help you understand the properties of similarity. Just like we've done before, we've done compositions of different types of rigid motions to help us learn about congruency. We're going to do the same thing with similarity. Similarity means we're going to look at things that have the same shape, same size. One's going to be bigger, one's going to be smaller, so it's going to be using a dilation. So let's take a look at our first example. Triangle DEF has vertices of D 20, E 14, and F 42. What is the image of triangle DEF when you apply the composition of the dilation of 1.5 of the reflection across the y-axis? So remember, we're going to do the second one first, which means you're going to reflect it first and then you're going to dilate it. So let's do that now. First off, we'll start by plotting our points. So we'll start with D is at 20. And then we'll go to E, which is at 1, 4. And then we have F, which is at 4 and 2. Alright, so we'll draw a line here, connect our dots. Now we're going to reflect it across the y-axis. So the y-axis is our line of reflection. So that means every point will get now moved over the same units to the right as it will be to the left. So it's 1 unit to the right, and this means E prime is going to be right here. F prime is 4 to the right, so it's going to go 4 to the left. Same y coordinate. And then D is 2 to the right, so it's going to be 2 to the left. So now we'll connect these dots, draw this triangle here. And so now we're going to dilate it. So at this point, what I want to do is I want to write down each of these points here. So I got D prime, because this is the points that are going to be dilated. This is going to be at -2 and 0. I have E prime, which is located at a -1 and a +4. And then I have F prime, which is located at -4 and a +2. So now we're going to perform the dilation of 1.5. So for each one, we're dilating it 1.5. That means we're going to get D double prime, and this coordinate is going to be 1.5 times a -2. So if you multiply 1.5 times a -2, that gives us a -3, and then times 0 is 0. So E double prime will be a 1.5 times a -1, which is going to be a -1.5. And then we have a 1.5 times a +4. That is going to be a +6. And then we have F double prime, which is going to be 1.5 times a -4, which we know is a -6. And then times 2, which is going to be a +3. So these are our new points. So we'll go and locate these. D double prime is going to be at -3, 0. So this is going to be D double prime. E double prime is at -1.5. So it's going to be, here's 1, here's 2, so it's going to be somewhere in between here. And we're going to go up 6. So here's 6 and a -1.5. So this would be E double prime. And then F is going to be located at a -6 and a +3. And once again, this is going to be dilated from the origin, so if it's not mentioned here, that it's always from the point here would be to the origin. So if we draw this figure now, connect our dots, and we have our new triangle. And so these are the new points. And so this would be your answer. So if you drew a line from the origin to the double prime points, it's going to go through the single prime. So if we drew a line to F double prime, it's going to go through F prime from the origin. And same thing with E and E double prime. All right, so let's take a look at the next one. Triangle LMN has vertices of L, M, and N. Suppose the triangle is translated 4 units to the right and 2 units up, and then dilated by a scale factor of 0.5. So with the center of dilation at the origin, sketch the resulting image of the composition of transformation. So pause the video now, sketch it out, and then write down the coordinates of L double prime, M double prime, and N double prime. All right, so we start with our original points here in the blue, L, M, and N. Now we are going to translate it, which means we're using everything 4 units to the right and 2 units up. Now, the last step is, so I wrote down the points of my prime points, and then I dilated everything by a half, which means this is a reduction. And so L double prime is at 0.2, M double prime is at 0.5 and negative 0.5, and N double prime is at 1.5 and 1.5. And you have this picture in green is what our end result is. All right, so now let's take a look at what happens when we're trying to figure out what is the rigid motion. What is the composition of rigid motions that's taking place to get from one figure to another? So in this problem here, we're trying to figure out how do we get from triangle RST to triangle PYZ. So as we look here, we're starting with RST. So it's going to be moved around over here, and then it's got to be getting larger. So it's going to be a enlargement. So how can we get this figure over here? Now we know that S has to match up with Y. So that means that this has got to be down here. So the only way we can either do that is rotate it around or reflect it across a line. Now, if we reflect it across a line, we have to do 2 lines, because this would, if we reflect it across the line Y equals negative X, the S would be over here. And we need the S to get down here. So what we're going to do, we can realize that this, one test I can provide is if I look and see if I go from S to Y and goes to the origin, I know it's a rotation of 180 degrees. So the first thing I'm going to write down is this is going to be a rotation of 180 degrees about the origin. Okay, so that's the first thing of triangle RST. So let's go ahead and perform that operation. So this is going to give us S prime, this will give us R prime, and T prime. So as we rotate this here, remember all we do is we take our points and we swap them. So before we write this down, we'll go ahead and write down what R, S, and T is. So R is going to be at a 1, 1. S is located at 1, 3. And T is going to be located at 3 and 1. Now, if you remember the rule for rotating about the origin of 180 degrees, you're going to swap your X and Y. Excuse me, not going to swap them, you're going to change the sign of them. So we have R prime, which is going to be -1, -1. S prime, -1, -3. And then T prime is going to be a -3 and a -1. So let's go over here and plot these points. So we'll start here in red. And this is going to be at a -1, -1. That is going to be R prime. Then we have S is at -1, -3. That is S prime. And then T is at -3, -1. And that is going to be T prime. So we'll draw our triangle. Now, the next thing we're going to do is we're going to dilate this figure. So we're going to now perform the dilation. So we're going to figure out how do I dilate it to get from this point to this point, or from T to Z. So if I look at this point here, Z is going to be located at what? Z is located at a -6 and a -2. So what could I multiply by the Z which match what? I guess I should put it in the right order here. Z would be down here with T. And usually I'll check about 2 points here, so we'll do R here in a second. And so how did I go from -3 to 6 and from -1 to 2? So that looks like I'm multiplying by 2. So I'm going to guess that my dilation is a enlargement of 2. So my scale factor is 2. So then I look at the R, which R is going to be at R and P match up. And so we have -2 and a -2. So if you look and see it, -1, -1, -2, -2, that means I've multiplied it by 2. So the scale factor does work for both. And if I wanted to find out what Y would be, I could check that as well. But once I usually do is I usually just check 2 to make sure it works. And Y is at -2, -6, and it means if I went -1 times 2 is -2, -3 times 2 is a -6. So to write our rule now, remember we always do the what we did is we rotated it first and then we dilated it. So what we're going to do is we're going to write this is going to be a rotation of 180 degrees about the origin of the dilation of 2 of triangle RST, put that in parentheses, is equal to triangle PYZ. So this is our rule that describes what happened here. Alright, so now I want you guys to try this next one. What is the composition of rigid motions and dilations that maps trapezoid ABCD to trapezoid MNHP? So pause the video now, work it out, and see if you come back and check to see if you got it right. Alright, so I do need to go back and make one correction here. I said it wrong before. The dilation is what should be written first, but it always comes second, so it should have been the dilation of 2 with the scale factor of 2 of the rotation of 180 degrees about the origin. This is example 2, part A. So go back and make that correction. So now, as we look at this next one, we're trying to figure out how do we get from ABCD down to MNHP. So we are obviously going to do a reduction. So the first thing we're going to do is we have to get this flipped around the right way. Easy way to do that is with a reflection across the y-axis. So we write the reflection across the y-axis. We have all of our original points, and our new points here are going to be at 6, 2, 2, 2, 1, -2, and 8, -2. So now we got to figure out how did I get from 6, 2 to 3, 1. And it looks like I'm dividing it by 2, or multiply by in half. So 2 to 1, 2 to 1 is the same thing. 1 divided by 2 is a half. So that means we are multiplying here by 0.5, which is the same thing as multiplying by half. So we write this as the composition of rigid motions. It's going to be a dilation of 0.5 of the reflection across the y-axis of ABCD, which equals MNHP. So once again, I apologize for making that mistake on that last one. It is you always put the dilation here that we did, that came last, so we put this here first in order. But you actually do the one that came second first. I know it's kind of confusing, but that's how we write those functions. Alright, so let's take a look at the last part here. Compositions of rigid motions and dilations map preimages to similar images. They are called similarity transformations. So two figures are similar if and only if there is a similarity transformation that maps one figure onto the other. So let's look at example 3. Is there a similarity transformation that maps PAQ to TNO? Okay, so PAQ into TNO. Now we can see by angle, we have two angles congruent to two angles, and so one of our rules of similarity was that by angle, we had side angle, side, and those are some of the ones we might use. So let's look to see, are they similar? And they, in fact, they are. So we can say that there is a similarity transformation. What's obviously happened is there's either been a rotation and then a dilation. So we rotated around a point, bringing this part up here, and then we're dilating it, or maybe a translation and then a dilation. So it's going to be an enlargement here to get this. So we'd say that these two triangles are similar by angle. And that's all you have to put. So let's look at the next one. Are these two similar? Is triangle JKL similar to triangle RST? So I need to pick some sides to check to see if they're similar. So JKL, we're going to look at JK. So that's going to be 10. So JK is going to match up with RS, which means JK is 10 and RS is 12. Reduce the fraction. That's going to be 5/6. So now we need to find another part. Okay, so we got KL. And KL will match up with ST. The last two in this one, last two in this one. So K to L is 12. And S to T is 16. So we'll reduce this fraction. 4 goes into both. 3 times here and 4 times here. These are not the same. So 5/6 is not the same as 3/4. So these figures are not similar. So these triangles are not similar. All right, let's take a look at the last one. The new company is using a computer program to design its logo. Are the two figures used in the logo so far similar? And if you look here, you can see everything kind of matches up. This one's just smaller than this one here. So we would say that yes. Okay. It appears to be a translation followed by a dilation. So it's been slid over and then dilated. Now, there can be more than just two. You can have several rigid motions that apply to some of these figures. Okay, so let's take a look at the last one. Are these two figures below similar? And explain. So if we look at this, is there any way we could take this figure and put it to this, or this figure to make it this? And for this, I can see that everything looks the same. So we would say that yes. And what have we done? We'd have to rotate this around 90 degrees, and then we would have to either translate it and then dilate it. So we'll say yes. there is a similarity transformation. So it could be a rotation, translation, followed by a dilation. All right, so this concludes our lesson on similarity transformations.